So we are back on the shell. Here's my Python for data science, my first directory, working directory. So we have the PWD here. We can see where we are. And let's do an ls, what was in this directory, right? We had the fruits.txt, we had the shakespeare.txt, we explored with them. Let's keep exploring a little bit more, simply with head and tail commands and some pipes and filters. I can first start by looking at the first 5 lines of fruits.txt. If you remember fruits.txt, it has some fruit names in it, right? I'll get the first 5 using head -5 fruits.txt, and I see that I got the top 5 lines. Then maybe it's good to see the first 5 lines of all fruit files that I have. In this case, remember that asterisk, our wildcard operator, we'll use that one. So if I simply say head -5, you see all those fruits files there, right? Fruits star. I'll see here fruits sorted with the first 5 lines. The apples are nicely sorted. Fruits unique. We don't have anything that has double names here because they're all unique names. And then we have the fruits.txt. So we did this in our last session. I can also pipe the output to a cat command, but it will show me the input it receives anyway. Just for completeness, let's clear our screen and say head -5 fruit star. Let's do all 3, and then we do pipe that into a cat, so we see the same output. Let's look at the last 3 lines in all the fruits files using the same logic. Stop for a second, think how you would use the tail command to get the last 3 lines. We will just switch the head command with the tail command here. So we can say tail -3 fruits star, and then we'll just pipe that into a cat. Here we see the last 3 lines of all 3 files. Let's clear our screen and imagine we want to now see the first and last 2 lines in a file. Let's say fruitsorted.txt. How would we do that? Remember that parenthesis, and we use that as a composite, 2 commands together and stitch them with a semicolon in one of our earlier videos. We'll use the same logic. And we can say head -2, tail -2, and we'll redirect the input to come from that file we wanted, fruitsorted.txt. Here we see the first 2 lines and the last 2 lines of that fruit sorted. We can also use another Unix command, and this is a new one, the paste command, to merge all fruit files into one file. So we'll use the wildcard with fruit star, but we'll say paste fruits star, and then I'll name a file called all fruits.txt. It's going to put all the outputs all the contents of the fruits file together into a file called allfruits.txt. If we cat into this file, we'll see that paste put the output side by side from each line. So this paste command in this way can be pretty powerful when creating tabular data from multiple files, and it's a pretty useful command for data science for that purpose. So now we know how we can do simple file manipulation using head and tail commands. Let's switch to our first question. Our first question was, what are the top 15 words used in Shakespeare's works? It's this file. Let's say cat shakespeare.txt, word count shakespeare.txt. We want to quickly know about this file, right? We see that there's 124,000 lines and many words and characters in this file. So it's a longish file. And there are also, when I look at this output, there are a bunch of blank lines, right? So that's definitely is adding to our line count, but it's complete. if you wanted to see the top of it, which is generally useful, I would pipe this into a more command, and I would see the file, just to explore with the file from the top to bottom if I wanted. I can get out using Q. Now let's apply our sed regular expression to turn each word into a line. So we see that every line here has a bunch of words separated by spaces. So we need to find that sed expression like we had in our introductory video that takes those spaces and replaces them with new lines. So we'll start with an s/ in our regular expression and with a /g for globally doing this through the file. In my Mac, the sed expression is kind of complicated, so I'll just switch back, not to just type it wrong. This is the sed expression for Mac. So now what I'm doing here is I have sed -e and started with s/ and ended with /g, and in between I have two / characters. The first part of the / is just a space, because remember I'm trying to replace the spaces. The characters in between the second and third / in my regular expression are really to get around some special characters in Mac. In another Unix shell, you could have just said \n and it should have worked. So let's try this. Remember, the top of my screen now shows the contents of Shakespeare.txt. I'm piping that file as an input to sed, SEDR stream editor, to replace those characters. Just think for a second what you would expect to see. Exactly, we will see. Hopefully, you were able to guess it right. We see each word in our input file on a separate line. So we now have all the words on separate lines. We want to pipe it into a sort to sort those words. So I have pipe, sort. Let's see the output of sort. It's going to take a little bit more time because remember we are going through each word twice now, right? So we'll have to wait for a second. Depending on your computer, this might take a little while. But now, here what we are seeing is we see all the words nicely sorted. We sorted the words, but if I go back actually to the beginning of this, I would see all those blank ones also. We want to remove those blank lines now. So to this pipe, I'm adding now, I'm piping the output of sort to another SED command. And it's going to get rid of those blank lines. And after those, we now have prepared our output stream from the pipe for the unique command. We got rid of the blanks, we sorted it. So let's just also run the unique command with the -c option and see what the output is. The bigger the file, the longer it takes, and which is one reason for us to learn Python. Here we are seeing all words. Now we got our output and the count of those words. Remember those words we sorted? Now we are seeing each word or a set of characters. Some of them, like U, has multiple characters associated with next to each other. They are counted separately. We could have processed our input further to actually make sure the U is U. U dot, U semicolon, U colon, they're all counted one. But we didn't go that far. So we count all of those separately. But what we are seeing in the Unix output now, there's the count for each word. How many times that each word occurred in our input stream. But it's not sorted, right? There's all the words are sorted, but the numbers aren't. So we want to now sort that numerically. So if I say sort NR, I'll actually sort that same output to list the counts in a sorted way for each word. So here we see, the last ones, it's in an ascending way, right? Maybe we should sort this into, pipe this into more so we could see the output stream a little better, because we want to see the top 5. We'll get that top 5 next. See that the sort is being done here. The word the occurred 22,000 something times, and the next one is 19,000, and it goes down from there. But remember that last couple in the end was used one time only. So I'm just going to go quickly. It goes down pretty dramatically after a while. But remember, our question was, take the top 15 counts. So instead of more, I should just use the head and head 15. So we want that top 15 counts from this output. And once we get this output, we will redirect the output into a file that we call count versus words. And later on, we'll use actually that file to redirect those top 15 into a plot using GNU plot. We got the output of our whole pipe here. As you see, we have that top 15 starting with the, I, and it goes down to with here. So I'm going to quickly do the same thing, but I'll pipe it into count versus words, just like we had in our example on our slides. So while it's processing and writing all the outputs into that file, I started saying a while back, this is why we also want to learn Python, because the longer or the bigger the data size gets, the slower doing it just on the Unix shell will be, or sometimes even the parallelized thing, use scalable execution. Python really gives us those libraries to do those things really more efficiently, data manipulation, visualization, analysis, and in general, every step of our data science process. Now we have it. If we just have, say, cat, count versus words, we'll see those same 15 lines nicely sitting in our count versus words file. Let's shelve that for a while and clear our screen and focus on our second question from our slides. The question there was, which users run the most processes on my Unix system? We haven't gone through it in detail on our slides, and I said in the live demo we'll go through this. Let's start thinking, I'm talking about the processes on my Unix system. And I need to know about, first of all, what processes are running on my Unix system. We'll use the ps command for that with some special options. And as we are using the ps command, I'll explain you which column is the users, what's a process, and things like that. So as I mentioned, I'll first have to list all processes by all the users and terminals. And I said I'm going to use some special options for the ps command. If we just say ps minus AEF, I'll have this long input stream, output stream, right? Let's actually pipe that into more so we can see the top of it. Here we see that the first line of the output is the column names for these, right? And the first command in there, and the first column in there, excuse me, is the UID. It's 4 unique user identifiers. I see, for example, 0 for the system or the kernel, and 501, if I go more on this, I'll see 501 running some UID, that first line here, 501, for example, for the identifier of the first user account created in my Mac OS X system. That happens to be me, right? To list all the users, how do I know, which ID belongs to which user, right? We can use another Unix command. And we can say list all in the user's directory with a unique identifier. So here we see those unique identifiers for different users. Remember, I said 0 was for the kernel. Let's find 0. The first one is the root here. And 501 was for Altintas, it's me. And 201 is the guest, and there are some special users that are running things in my system actually for me in the background. Okay, so let's go back to our PSAEF more. We want to cut those user identifiers from each process, so we will use the cut command for that. Because our question said which users are running the most commands. So we'll first find those user identifiers and output those. And then we'll sort each line and do the unique just like we did before. So let's add to our pipe. Instead of more, I'll say cut minus C 3 minus 5. This says cut with the section from character 3 to character 5, which is roughly our user identifier. Okay? If I go through this output in a text file, that's what I would see. Then let's pipe it into more. So what we are seeing here is only the user identifiers, right? From all those processes that are running, I cut those user identifiers, and we see 541 and 0 happen a number of times. So we want to cut how many unique user identifiers there are and how many times they occur in my system. We used this exact same logic for our Shakespeare example before. What we've done is we sorted each line and found out how many processes each user ID is running using the unique command. So if I just say this, I'll see, for example, user ID 0 is running 115 commands, and user ID 541 is running 220, UID. Since we didn't do a lot of text cleaning, that first line, UID line, is still in my output. That makes sense. So we are sort of going to ignore that for this example. So now that we have the unique number, let's sort them numerically, because which users are running the most processes was the question. So we've done the same exact numerical sort a few minutes ago, so we'll use the same one. So we now know 501, which is my account, is running the most amount of processes. Now that we sorted each user and the number of processes, we'll finally use head to get the top 3 users in terms of how many processes they are running. We'll just pipe the whole output into head minus 3. It's going to give us the top 3 lines because our original question was that. A side question we can answer is how many processes I am running. So I don't have to sort the whole thing. I know my user ID is Altintas, and the number, unique identifier for that user ID is 541. We just went through that. Instead of counting all the output of sort with unique, we can go back to this sort step, and we can use the grep command. So, and then after finding all the lines using grep that has the UID 501 in it, we can use the word count with the -L option, and we can find that same number for the processes I'm running. So I'm going to change this to grep 501. So it's going to look for that 501 pattern in the input stream for grep, and then we'll pipe that into WC -L. It's going to give me that first number here, which is 221. there we go. I'm running 221 processes right now on this Unix system. We've seen something different here, right? We've seen in this output we got me running 221 processes, and in this one that we did the head command, at that moment I was running 222 processes. So a process was probably active and it finished, so my process count went down to 221. So you see that Unix is an active system. A lot of things are being taken care of for you in the background. So we see an example of that here. So let's do another side note here, because we use the process command ps. And let's check the output of it one more time. Let's just do this, ps minus aef. I'll first clear my screen for this one, for clarity. And I'll say ps minus aef. And let's pipe it into more so we can see the top of that. Okay, there we are. So we see here things like PID, PPID. Let's spend just a few seconds on what these mean, right? In every Unix-based system, there's a process with PID1, and you see that here. Root runs that PID process 1, and it becomes a parent process, PPID, for many other processes, right? This process is called actually the grandparent of all the processes in the Unix system. And depending on your Unix system, it's either launch HT or init, its name changes, but it is really the first process, the grandparent of all the processes. And the kernel, the root itself, has a PID of 0. Okay? In addition to a unique PID, each process also have this PPID, parent process ID, that tells which process started it. The PPID is the PID of the process's parent, and the parent processes start new processes as sub-processes. So after this quick process overview, let's go back to our first question again and try to plot the results of the pipe. Remember, let's clear our screen. Remember, we used count versus words, the file, to save those results, the counts of each word, top 15 words, right? So this was our pipe, and we got the outputs. Now, we will use GNU plot to actually plot these numbers on something like a bar chart. So when I enter GNU plot, I had to install it on my Mac. I see my GNU plot interface. So I'm going to save actually the plot into a PNG file. So I'll just say set term to PNG. So save the output, the image that comes out of the graph, into a file with a PNG extension. And now I'll say output file will be something like word counts.png. I'm just coming up with a new file name here. And I could do a number of things to set the parameters of, let's say, the width of the bars in my chart. I can set style to a histogram style. And I can choose to do a solid fill, so I can actually keep improving my style here. Fill solid 1.0 with some border extensions. So don't worry about these lines yet, because we are not using GNU plot. I'm just showing this as an example. But hopefully, if you're interested, you can go explore further. So now, what we are going to do is start plotting that counts versus words file that we created. So we'll say plot and getting some inputs here. We were going to use our counts versus words. Words is our input file, and using some labels. So now actually when I go back to this directory, let's exit our GNU plot. Ls, our file name, if you remember, was wordcounts.png. I'll see wordcounts.png file here. I need to go back to my directory, Python for data science, my first directory, and here we have wordcounts.png, as you see, and here we have the, I, and all the rest of the words. Remember, the was 22,000 something times, and it went down to 19,000 and onwards. So we do a quick data plot to see how it's progressing in terms of word counts for the first 15. Here we see, in essence, that bar chart that we just created. Very simple and definitely needs some improvements, this example, but we see how we can use Unix command and how powerful and quick it can be once we master how to use the pipes and filters with some commands and data and text manipulation. This is the end of our Unix overview. Next, we will review how we can interact with these commands from Jupyter Notebooks after a quick review of the notebooks and their ability to ingest and interact with various programming languages, one of which happens to be Unix.